coming. I'm really excited to have James Defense. So James was in my lab since 2019. Has been working on a range of continual learning problems. Since then, has taken
We're using the word lifelong learning today.
Oh, sorry. Too much terminology. He's the expert now. So. Since then, he's kind of taken off like a rocket ship. I think he's been doing not just amazing research, but also in organizing like a 24-hour straight unconference and doing a bunch of other kind of service to the community. So with that, I'm excited to have James speak. I guess for administrative purposes, so we're gonna have him give a presentation. If you can kind of keep it to clarifying questions during the presentation. And then we'll have a public question session, and then after that, we'll kick everyone out, and you all can take the food, and then we'll have a private question session. So, cool. Thank you. Take it away.
Awesome. Well, thank you everybody for joining. Today I'll be talking about my PhD thesis, lifelong machine learning without lifelong data retention. So what do I mean by lifelong learning? This describes a process of which we acquire new knowledge and new skills in a continuous fashion over our lifetimes. Take, for example, this young starving dog we adopted who turned into a happy, healthy dog and will one day become a mature, wise dog, hopefully. The key question we should ask is that we as humans and animals can naturally have this lifelong learning processes. Shouldn't our machine learning models be able to do the same? Let's ask ourselves what happens. Let's say in a typical machine learning paradigm, we train some machine learning model offline in a data center and we deploy it out into the real world. And sometimes we find that our model works good on some types of data, but new and unseen data it may struggle with. So this asks our Dolly generated expert here to ask the question, my model has not seen this type of data before. How do I fix my machine learning model? So question. You deploy a machine learning model out into the real world, it sees new data, and you need to collect that new data and update and refresh the knowledge of your machine learning model. How are we going to go about doing that? Well, you may think, let's just train the model only on all of the new data at once. We're going to have this phenomenon known as catastrophic forgetting, where machine learning models catastrophically erase and destroy the knowledge that they had previously acquired on old data. Okay, let's just take the new data, combine it with all of the old data together, and train the model with that combined. Well, the problem there is you're going to have really big inefficiencies. If we have to, every time we refresh the model's knowledge, retrain it from scratch, that's going to cost a lot of money in compute. Plus, there's some data that may have data privacy concerns that cannot be stored long term. But based on the title of this presentation, if you guessed lifelong learning, you were correct. So why does it matter? First, efficiency and scalability. As I mentioned in the past slide, we're having to continuously update our modern machine learning models in the real world and refresh them with new information. If we have to retrain it from scratch every time, that's going to cost a lot of money and a lot of compute, cost of both financial and the environment. Also, robustness. A model that is continuously learning to adapt to new concepts is going to be more confident when it is confronted with new and unfamiliar types of data it may see. And finally, a big focus of this presentation also is privacy. So I'll go into that a little bit deeper. The AI processes is using sensitive user data in a lot of our day-to-day activities, such as your smartphone is now using machine learning to learn about you. There's a lot of data retention policies that make it such that we can't, there's privacy risk. We can't store all that data offline about you somewhere in a data center, or rather you shouldn't. Maybe in America, but in Europe, they definitely don't, because there is certain laws even that protect these type of user data rights. But here's the crux. Lifelong learning, or these successful lifelong learning approaches, they require storing data long-term for replay to replenish your model in the future and not catastrophically forget. So that's the problem. We need to be able to find replay-free approaches that don't store your data long-term in order to enable ethical and legal lifelong machine learning. So, I mean, if we can't use replay data, why don't we just not use replay data? So here's the problem. So back when we started this PhD, we had a work actually from our lab showing that for the difficult types of problem settings we're looking at, I'm showing you a table here where methods that store replay data have numbers close to 100, which is up or down accuracy when they use stored memory data. And all the methods that don't store any replay data have failing performances. And the conclusion was that we need rehearsal types of methods perform much better than all types of other continual and lifelong learning methods. Another paper right out says the same thing. They had a stronger statement saying that regularization-based approaches fail and that replaying representations of data seems required for solving lifelong learning. That brings us to our thesis statement of this presentation. We're going to show to you today that auxiliary replay data and/or strongly pre-trained models can replace training data replay for lifelong machine learning. In the first part of this presentation, we're going to show that pseudo replay data that we can leverage both from model inversion and our agent's environment can replace the replay data for replay. After that, we're going to show you that we can use pre-trained models instead and continuously adapt those without having to store long-term replay data. And finally, we're going to go into a really cool recent example where we take really amazing text-to-image customization models and show that we can customize these in a continuous lifelong fashion without having to store your private user data on long term. Great. So I just had a little bit of preliminary before we jump into the technical content of today's talk. I talked and motivate at a high level this lifelong learning problem. We're going out and continuously acquiring new skills and knowledge to update our machine learning. But how do we talk about this in an academic setting? What we're going to do is we're going to create data sets that we train first image classification, which is a problem setting where you just have data coming in, it goes into the machine learning model, and an output prediction comes. Like this is an image of a dog as an example of a classifier. And to test this lifelong learning, we're going to take data sets with different types of informations. Like the task 1 may be dogs versus cats, task 2 may be whales versus dolphins, and we're going to send our agent through each task sequentially to learn that data. And key is when we're learning a task, we do not have access to the past task data. So in here, when I'm in task 5, I cannot go back and revisit task 1 through 4. However, I should still be able to perform well on that data. So we're going to talk about two different kind of metrics to keep in mind. One is after we train on all 5 tasks, what is our average performance on all tasks we've ever seen before? So after training task 5, we should still be able to perform well on task 1, 2, 3, and 4. We're also going to evaluate specifically how much we forgot earlier tasks. So in this case, after we've trained the most recent task 5, we have no access to task 1 through 4. I'm going to evaluate my performance on task 1 at the current time and compare that to how well I did on task 1 when I first learned it and see how much did we catastrophically erase our information? How much did our performance degrade over time? And the problem we have is we can create a very naive model that's really good at learning new tasks, but it's going to forget really, really badly and catastrophically erase information. At the same time, we could think of a naive approach and model that's going to not forget at all because it's not going to move, but at the same time, it's not going to be able to adapt and have plasticity to learn new tasks. This is called the plasticity stability dilemma. In lifelong continual learning, we want something that is going to be good at new task adaptation, but bad or low at forgetting. How do we go about doing that? This is just a very high level approach of the existing strategies out there before we dive into our work. One way you can do that is you can regularize the model parameters themselves. So we have a machine learning model learning a new task in. I can retain a frozen copy of the old model, and I can simply add a regularization penalty to keep the parameters of this model close to the parameters of the old model. I just penalize the parameters from moving too much when I'm running a new task. I can also do a different kind of regularization. Instead of regularizing the model itself, I can take some data and feed it through both versions of the model to get model predictions. And then I'm going to keep a tight boundary where I want to keep my predictions consistent on this data. So I don't regularize the model, I regularize its predictions to be close on the same data. Finally, we could just freeze the model and make it bigger, and then only learn that bigger new model capacity and keep everything else frozen in the past. So these are kind of 3 high-level ways that we're going to go about lifelong adaptations to our machine learning models. Great, so that starts our introductory section. Now I'm going to go into the technical meat and contributions of our work during my PhD. We're going to start looking at how can we find auxiliary pseudo data to use for replay so that we don't have to store and retain potentially private user data. So the first thing that we looked at in my PhD is synthetic data created via model inversion. What this means is, hey, I don't have access to my old training data, but I can do some pseudo optimization and try and create fake synthetic data that the model has seen before. So all you need to understand there is we're going to try and use some fake synthetic pseudo data instead to replay. What we find here in this is a first contribution of our work. We diagnosed there was a bias problem. What I'm showing you here is embedded data from an old task called real task 1, this little red line, synthetic data that we created to represent that same task with the blue horizontal line, and we're trying to learn this new task X, this green X. And what I'm showing you here is that the machine learning decision boundary, rather than separating T1 versus T2, it naturally, with existing methods, creates a decision boundary around real versus fake. So when I'm trying to do T1 versus T2, I'm naturally using the pseudo data. The model instead is learning this decision boundary, real data versus fake data. So that's a problem. So I won't go into the gritty details of this, but the TLDR is that we created a method to have the same properties of lifelong knowledge distillation, but circumventing this bias decision boundary that we discovered. Again, the details, it doesn't matter, but the main thing is we contributed a new type of feature distillation loss that is going to mitigate forgetting while avoiding this decision boundary problem. We diagnosed the bias correctly by having a specific way to do cross entropy loss on the model's new task data. And then we have a fine-tuning regularization just to keep old and new tasks balanced. And the main idea here is we were able to circumvent this biased decision boundary and turn it into a new clustering feature space where now the real data from the new task is in different clusters that's far away from the old task data, and the real and synthetic data, the red and the blue, are now overlapped within each other. This is a much more desirable feature plot that we would like to see. We can look at this from a more practical perspective where we just measure our performance on actual academic benchmarks. Here I'm showing you some plot where a metric that higher is better. We want ours to be as high as possible on this plot. The red line at the top is going to be the true upper bound. We had perfect knowledge, no continual learning. This is what our model would perform as. And our method is the thing right below it, the dark purple red X's. That is going to be our method's performance. And you can see compared to the prior state of the art at this time, we have a wide performance gap increase. So the takeaway here is that we establish a new state of the art, but we find that we are able to use pseudo data replay for lifelong learning and completely eliminate the need for storing real training data. Now, the problem with this process is that you may imagine, how do we make that pseudo data, that's synthetic and fake data? You might think about it a little bit and say that might be really expensive to do. Every time that we're trying to create new data to replay with, we're going to do this optimization to invert and create this fake data. So what about a different option to use pseudo data for replay instead? And we had an idea. What if we did realistic replay from an agent's environment? Let's consider the setting where our machine learning models actually deployed out in the world, and there may be unlabeled or unsupervised data out there that we can leverage to mitigate our catastrophic forgetting rather than labeled stored core set data, rather than pseudo inverted data. Now, the research question is not the naive question of, oh, does it work to leverage the unlabeled data? But we particularly looked at how does the correlation between that unlabeled and labeled data affect replay in continual learning? Is that unlabeled data going to be uncorrelated data from the internet that's just being downloaded with no connection to the current data we're learning? Is it going to be something from the agent's environment where we're learning cherry blossoms and there's going to be other types of plants that are in the unlabeled data? That's what we care about. The TLDR of our method is that we have a new continuous form of out of distribution detection. That means telling you how confident that we've seen this data before. And we also have a new type of semi-supervised distillation. That just means a loss that leverages both labeled training data and unlabeled data that has not had any human annotations with it. So first we find that when there's no correlations between the labeled and unlabeled data, we actually don't need any replay at all. We can get incredible strong performance. On this plot, I'm showing you a bunch of state-of-the-art lifelong learning methods that do store training data for replay. And as we go from the left to the right on this plot, they're having more and more replay data. So as they get more replay data, the performance is getting better and better. Now, the prior state-of-the-art that does not require replay data is this dotted purple line right here around 60. Our method is almost 80%, much stronger performance without using any replay data at all. And methods that state of the art at the time required much replay data just to match our performance. The takeaway here is that we don't need to store replay data if we have access to uncorrelated, unlabeled stream, like such as downloading things from the internet and using that to replay. Now, what happens if we're actually out in the environment, we don't have internet connection, we have to use data that we actually have available to us? We went and we evaluated many different realistic settings where we assumed positive and negative correlations between our labeled training set data and our non-human annotated data that's just available out in the wild. And we found that the prior state of the art in this curve, where again, higher is better, is a screen line. We found that this method that worked really good in the last plot, it was the second place to ours. We found that when different types of correlations exist in the environment, certain assumptions of the method break, and it has drastically poor performance. Meanwhile, our method over here on the top rightmost curve, no matter what, under several different types of correlations that could exist, we always found that our method was robust to these different types of correlations and robust to these different problem settings. So the takeaway here is that we do need some type of small core set replay when we have all these types of correlations that may exist, but our method is going to be the most robust to different ways these correlations may exist in the data. So that finishes as part one of the talk. The key takeaway here is that we can use auxiliary data to replace training data, replay, and lifelong continual learning. There is a caveat though. The types of performances we got were state of the art, which is great for an academic paper, but the performances we got were also not good enough for practical real world applications. So we pivoted to a new type of paradigm where we instead say, can we find something else that can replace this type of thinking so that we can actually have competitive, strong methods that may have real world applications. So we turn to model pre-training, where rather than starting with a randomly initialized machine learning model, we start with a model that's already seen a lot of data, and we continuously adapt this model to new and emerging concepts that it may see. The assumption here is that a strong initialized weight space is going to allow us to have very strong performance and opens up our arsenal to a lot more types of methods that we can use. So this comes into a thing called prompting for lifelong learning. Many of my family knows what ChatGPT is. Now I can tell you what the T stands for. It's this architecture called a transformer architecture. It's a type of machine learning model that's very useful and hot these days. And what we're going to do is we're not going to touch a single parameter in that model. Instead, we're going to have these things called prompts, where some input comes in, it matches to a prompt, which is a tiny little tensor, and that tiny little tensors are inserted into the model and trained. So we don't touch a single parameter in the backbone. That's a pre-trained model. It does not change at all. We're instead going to have these tiny little insertable prompts that are put into the model in different spots, and that's what we update. That's what we learn with gradient descent. I mostly avoid equations in my presentation today, but I do need to talk precisely. So I will say that the key block in this transformer is called multi-head self-attention. And what this is it's just a series of transformation matrices that act on input data. The ones that we care about are these projection, query projection, key projection, and value projection. And the reason I want to talk about this in a principled manner is to explain what prompting is. With prompting, what we do is we don't touch these weight matrices at all in the model. Instead, we are pre-appending the input to this function with these tiny little learnable tensors that are updated instead of the model backbone. Prior work has found that this is much more robust to catastrophic forgetting and much more stronger for continual lifelong adaptations of the model. And the research question is, how do we select a prompt that's input conditioned and update the prompts in a continual learning manner? As you can see from this figure, when an input comes in, it's matched to a prompt, and that prompt is what passed into the model. So the model is going to be a little bit different depending on what data is actually presented to it. So how are we going to do that in a continual lifelong fashion? So what prior work is going to do, they're going to have a key query mechanism where some data query comes in, it matches to its closest query or with a clustering optimization. So simply, here's my value, what am I closest to? And based off who I'm closest to, that is the prompt that's going to be passed into the model. So I come in, I only find one prompt that I'm closest to, and I go with that prompt into the model. The problem with this is that the gradient flow from the model will be optimized with back propagation. You can only go back to the prompt space because one prompt per image, but we can't do anything with these clustering keys. That has to be learned in a separate optimization with a clustering-like optimization. And one thing with deep learning and AI we know is that backpropagation and gradient descent is the key to success. So we completely reimagined this for our contributed method. What we do instead is rather than having a one-to-one matching of query input to prompt, we now say, hey, how close am I to each prompt? That's going to be a weight of closeness, and I'm going to have some contribution from every single prompt with a weighted summation coming in. So rather than saying I'm closest to prompt two is going to be passed to the model, I'm going to say this is actually going to be a component dimension, a new dimensional axis where I say I'm really close to prompt two, so prompt two is going to have a strong contribution to my final prompt. I'm kind of close to prompt five, so prompt five is going to have a little contribution, and I'm really far away from prompt one's key, so prompt one is not going to have any impact on my final prompting, my final prompt that's passed into the model. And this has very nice properties. We leverage both orthogonality, which allows it to be a growing orthogonal basis, as well as you can see, the gradient from the model can go back to every single parameter that we have keyed here. So everything can be learned end-to-end optimizable. So the too long didn't read here is that we expand and reimagine prompts in a new dimension, an optimizable component dimension. And that's going to be the key to our success. So this is some results for this method. We set the state of the art for 0 replay image classification compared to prior works at the time. On the far left, this is going to be the upper bound target. This is a model that had access to all of the data from the start, no lifelong learning. This is the performance they were able to get on this data set. In the blue here, we can see the prior state of the art, 71.49. And in the far right, we have two different results for our method, and we closed the gap between the prior state of the art and the upper bound by over 50%. So we're getting closer and closer to upper bound performance as good as we possibly could get with this new dimensional component analysis. So the takeaway is it's state of the art, at least at the time of this paper, for this problem setting. But from a research perspective, we want to understand truly why that's happening. We don't want to just, here's our method and it works well. Are they doing the windows today?
Temporary thing.
Okay, cool. So question is, why does total prompt work? Well, I told you we're optimizing these little tensors in our model. And I'm showing you here that with different types of methods, as you make those tensors bigger and bigger, there's actually no improvement gains for any of the methods. So making the prompts bigger is not going to help these methods. Instead, it's the key contribution for our method is that we have a new dimension to expand. We contribute this new component dimension. As we increase the components of our prompts, we can see we have returns that come. That's where all of our gains and strength comes from this new created and contributed dimension. So up to this point in the talk, we've been talking about image classification. What about something more interesting? And nowadays, we care about things like vision and language, these cool multimodal models that exist out in the world. We were able to continuously adapt an image classifier model, but what about a more advanced type of model? So we're going to next look at vision and language models. We first propose a new benchmark that's going to allow us to closely study the phenomenon that we care about. We create a benchmark that is doing vision and language types of attributes. So for example, if I give a photo, I want to know, am I on the couch or is the couch on me? Those kind of things that actually vision and language models struggle with, these types of relationships that exist in a picture. And we imagine this phenomenon where OpenAI releases their image-guided GPT-4, they collect training data, and suddenly they realize, hey, we're really underperforming on these types of spatial relations or this type of images. Let's collect some data and update our models. How do we collect the data and update the model in a lifelong fashion without having to continuously retrain it on all of the old data? So how are we going to go about doing that? So the cool prompting approach we had in the last paper, unfortunately, was not powerful enough to tackle this problem. So we had to look elsewhere. Instead, we proposed to use low-rank adapters, also known as LoRa, which we were the first to do this for these big vision and language models and the first to do this in a continual learning fashion. So what this means is a very cool principle. When I'm trying to update a matrix in my machine learning model, Rather than directly change the parameters, I'm going to model its differential as a product of two low-ranked tensors. So my change in the weight is not going to be a full matrix. It's actually going to be modeled with two low-dimensional tensors multiplied with each other. And I'm going to do this for when I'm running the first task, and I'm going to stack it and do it on the second task, and so on. And why would we want to do that? First, this low rank adaptation, we actually find to be very robust fine tuner, which is great for lifelong learning. As we don't overfit on the current data we're seeing, we actually have less ability to forget our future tasks. But more importantly, it's this really cool things that one, it's memory efficient. As models get bigger and bigger and bigger, and you're trying to fine tune it and fit it all on your GPUs to actually train it, this low rank adapters gives us a way to actually fit it on our GPUs and adapt it and change it, because we don't have to store the full matrix. We can just store these two low rank tensors. Furthermore, it's great for lifelong learning because it's almost like a cheat code. We can store, since these are so small, we can store every past copy of our model in memory and go back and revisit that copy whenever we want for free supervision and free guidance for learning our new and current task. So what do I mean by that? Let me show you an example. This is how we actually implemented our method to use exactly those basic fundamental scientific principles we said on the last slide. How do we go about and implement that? So I'm going to show you that right here. Let's say we had some training data. This is a text and image pair, a handsome dog on a couch. What we're trying to teach our model now is spatial relationships, that the dog is on the couch and the couch is not on the dog. So we're training our new part of the model, spatial relations, and we just finished training our model on colors, such as a white fluffy dog on a couch. So we're going to pass it through the data through, get some classification loss. As I mentioned previously, we're not going to change the model weights themselves, but rather our model is imagined as a summation over low-ranked tensors. So everything else is locked, and we're only running a new low-ranked product to be our model adaptations for this task. And here is the key innovation. When we're training on the new data and the new task, we can now go and create pseudo data. We can go revisit and load into memory our old model for free. We just don't use this current LoRa. We can suddenly revisit the old model and do some adversarial optimization to create new data for the old task. So rather than storing the data that we learned in task one, we can very, very cheaply go and create pseudo data from task one using this low ranked LoRa implementation, and voila, now we also, for very, very cheap, are able to distill knowledge from our old task and old models using these low rank adapters and adversarial perturbations on our current data. And this works quite well. Results wise, we see on the left, blah, 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 a whole bunch of other really great methods that did not work very well in this setting. And on the far right, we can see our method has strong performance for zero replay in this continual learning benchmark. So I'll recognize the takeaway here is that we proposed a new benchmark, and then we are the best at that benchmark. Yay for us. No. The real takeaway here is that this is a really, really awesome finding that this layered stacking of LoRa and memory to adapt is a really, really strong lifelong learner for strong vision and language types of models. So far in this talk, I have discussed, can we use auxiliary pseudo data for lifelong learning? We said, yes, we can, but the results are state of the art, but not that great. Then I said, can we do pre-trained models with these types of prompting and low rank adaptations to the pre-trained model? We said, yes, we can, and it works quite well. But these are still, what about something that you care about, you, the audience member? We looked at a more like use case for the most recent work of a really awesome problem study called text to image customization. So what does that even mean? Hopefully you're familiar now with things like stable diffusion. They're models you can download on the internet. You text a little prompt into it, and it creates an image of that for you. It's really nice. I actually created some figures in this presentation by going to these online and saying a stock picture of X, and it would create that picture, and I could put it right into my PowerPoint. What if you want to customize it to your own data and your own concepts? So I could go in with a stable diffusion model, and I could say, hey, I want you to learn this combination of this prompt means this dog. Train it. So now I can go back out and say, hey, I want a photo of this dog in the style of a cartoon. Suddenly I can get my own dog stylized in this cartoon, because I have my own customized model. What about in a continual fashion? What do I want to add my sister's dog and my parents' dog to it? Do I need to retain all of the data that I showed it in the first and retrain every time? Not only do you have to retain data, after we get to concept 10, concept 11, suddenly we're going to have a whole lot of retraining costs where we're going to have to, it's going to take 10 times more iterations every time to retrain the model from scratch, even if we stored all the data. So instead, it's very natural to have a lifelong learning solution where we can just continuously show it new data as we want and update the model without it destroying prior information. I want it to be able to learn my sister's dog and not destroy Watson's ability to create Watson images. So I know, quick little thing on prior works. How do people customize these diffusion models? You may not really need to know the details of this for the presentation, but I'll discuss it just so we can talk about it in a good manner. But the takeaway is that at the time of this first paper, the state-of-the-art way was to fine-tune a specific part in the stable diffusion model only. It's called the KB projection matrices in the cross-attention module of the diffusion model unit. And the important part here is there's a specific part of the model that's most sensitive to changes for these concepts. We're only going to fine-tune in a regularized way that specific parameter in the model. The prior works have done this, and we want to imagine them in a continual lifelong fashion. The first way we could think of that is, hey, let's just train it on the first concept, then train it on the second concept, and so on in a sequential manner. Another way we could do that actually is just train different models for each concept and try and merge them together in a closed form optimization. And we try to do that with these really cool things that we're looking at today. With variant 1, we have a problem, as we discussed today, called catastrophic forgetting. So when I trained on Watson and I trained on my dad's dog, which is also a white fluffy dog, I found empirically that the model is going to catastrophically forget how to know Watson. Furthermore, on this closed form optimization, we found the max where we can only do about 3 to 5 fine-grained concepts until it just suddenly collapses in performance. And furthermore, memory costs, because you have to store a copy of the model for each task, so that's going to be expensive from a memory perspective as well. So we are not satisfied with the existing solutions, motivating us to think of a different approach. So we're going to come back to this LoRa thing, this low rank adaptation in a continual manner. And this worked really good last time. I'll first mention that the very naive way that you could think of, which is just, okay, it's a generative model, why don't I just generate pictures of Watson while training, the next dog? The problem with that is that artifacts that appear in this generative process start to multiply. We found that after about 10 to 20 tasks, suddenly they get really, really collapsed artifacts into our model. So this was not a possible solution. So we came back to LoRa, these low rank adaptations. Now, let's say that we trained on a first task of our LoRa, which again is the product of 2 low rank tensors. And this tells, okay, this weight needs to move with this type of parameter values. Well, if you imagine we're training on similar types of fine-grained concepts, I told you there's certain parameters that are sensitive and need to be updated the most. So it should be no surprise that on the task 2, it's going to tell it to move in the same spots in the model. And as you can imagine, if we tell it to move in the same spots, we're going to have interference where the LoRa's are going to be trying to tell it to move in different ways. So we actually had a very nice and simple solution for this. We tried state-of-the-art regularization methods, things that worked for continual learning, but what worked by far the best was a very simple self-regularization, where we had a Euclidean penalty that simply says, when I am learning W2, I want to not grow in the same spots that I learned in W1. This penalty says W2 should not grow where W1 grew the most. And now you can see W2 is forced to learn a different spot in the weight matrix. So now we've gone from high interference to minimal interference with our model. So let's take a step back and look at what our full approach, using this, leveraging the ideas we said on the previous slide, how is that going to work from a full perspective? On the left here, this is the yada yada diffusion model. It's a really cool model, but for the purpose of this presentation, not really important. Just as we said last time, we're only looking at a very specific part in the model that needs to be changed. It needs to be continuously adapted and fine-tuned for our problem setting. One important thing is that these types of customized models, you actually learn a word associated with each concept. These are things called custom tokens. So in the feature space, in the gradient space, in the embedding space, we are going to learn certain tensors that represent fake words for each image. So this person one, actually we learn a word that represents them, that goes into the model through backpropagation. Person two learns a word that goes to person two, and so on. And these words are just trying to capture key concepts and instructions so the model can recreate the pictures with their word. But with fine-grained concepts like people, that word is not enough, which is why we have to go into the KV projection matrices and actually continuously fine-tune and adapt the model to the concepts. So as I mentioned on the last slide, these adaptations are going to be a summation of low-ranked tensor products. Just right here is saying exactly what we said in the last slide. Each weight is going to start with its frozen backbone. Then we're going to add frozen copies of low-ranked tensor products, and we're going to keep doing this. So right now, when I'm learning this most recent person, everything in the model is frozen except the low-ranked Bora tensors that I'm running for this person. And as we mentioned, the key innovation here is a simple self-regularization that mitigates and prevents interference in the model fine-tuning. So results-wise, on the top left, what we've done here is that we've trained on 10 different people. Train on person one, train on person two, all the way up to person 10. After I've trained on 10 different people, I'm asking the model, hey, go back and show me a picture of person one, show me a picture of person five, show me a picture of person 10, exactly that. And even though I haven't seen person one in a long time, we want to make sure we can actually recreate them with our model. In the top left, this is what we want. This is the ideal desired outputs of our model that are not, these are not continual learning, this is a target. In the top right, we see some existing methods such as this right here, textual inversion. All this does is it learns that customized word for each person while keeping the model frozen. And we see that does not have enough properties to actually adapt to these people. There's things up here in the top right that either have catastrophic forgetting or this deep generative replay that has all these artifacts emerging. In the bottom left, we can see this custom diffusion method, which actually does a lot better than full fine-tuning of the model, or these things in the top right, but there still is catastrophic forgetting in this method and this method, and the one in the middle where we merge the different models together. As I mentioned, as we get to a certain number of people, suddenly we have these weird people coming out that are kind of combinations of all the different people together. So these are not going to be satisfying solutions either. Thankfully, we have our method on the right where we see we can create realistic representations of each person we've seen before and matches their identities very, very well without catastrophic forgetting. We have a paper online that has quantitative results and tables with metrics that show the exact same story that I told you now. So this brings us to the last part of the talk. This is past my proposal work, what I've done since that for my committee. So there are some problems with this method I just told you. And actually, when I talked about our paper with people, they all said the same thing. How many people can you learn until you run out of space? I showed you results for 10 people, but how do we scale that up? And they're completely correct. There's that self-regularization mechanism. And as you imagine, as we keep regularizing it more and more and fitting more people into those model adaptations, at a certain point, we're not going to be able to learn any more people because the regularization will be so strong, the model will not move. And I showed exactly this right here. As we started, the model moves a lot at first and it slows down. And suddenly after about 10 people, it's almost a flat curve. The model is not changing at all. We have saturated our ability to learn new concepts and new people. So how are we going to circumvent that? How are we going to expand our scalability capacity? So we had two contributions. The first is actually a very simple and intuitive idea. What if we put binary masks on top of our adapters? So the idea here is we want to have the most precise surgical fine-tuning possible. We only want to modify the model exactly where it has to be modified. So we want to sparsify these updates with binary masks. And suddenly you can see here that we've gone from minimal interference with our Seale method to no interference because we masked out all the non-important updates to the model such that there was actually zero overlap between the adaptations. That's a concept that we want to utilize the sparse types of updates on top of our low rank adapters to minimize interference and allow us to learn scalable solutions. How are we gonna do that exactly? So the prior method is the Seale method. I said right up here, we start with the frozen model weights, and we add all these LoRa adapters, a summation of low ranked tensors. What we're proposing exactly is to add masks of the same dimension as W. They're going to be binary and sparse masks that are going to find the exact spots of that LoRa output to mask so that we have the minimum number of changes possible. We want to only update the model exactly where it has to be updated in order to achieve its desired performance. And we only go in the exact spots we need to, there's less room for interference and more room to pack more and more concepts over time. Now, you're probably asking yourself, this is a discrete binary mask. How am I going to optimize through this process? That is, we're going through a categorical binary distribution. This discrete sampling, we actually can't back propagate and learn through gradient descent. And that's where the Gumbel softmax comes into play here. This allows us to relax certain constraints, and it allows us to actually learn true discrete binary masks with back propagation. I'm not going to go into the hard details of that. The main thing is this changes the actual parameters we learned. Each of these masks is samples from the Gumbel softmax, and we have these masks that we learned. These G are samples from the Gumbel distribution, and this tau, which is our hyperparameter that controls how much we relax the discrete constraints. And one last contribution we're going to have here. We found that with these binary masks through the Gumbel softmax, we had remarkable performance. We could scale up to even 100 tasks. It was really, really great results. The problem was these were incredibly difficult distributions and things to learn, and it took a long, long time to optimize it. So we were able to do our Seale in 200 iterations. Suddenly we needed 2,000 iterations in order to find exactly where we can modify the model, those exact precise spots. So how are we going to fix that? So this contribution, we're the first to do it in this way, but we're not the first to do this ever. And we think of this more as a necessity in order to get our discrete masks to work, to get our sparse discrete masks, we need to do this. So rather than optimize tensors, which is deep, deep down in the model, we put these tensors and optimize them, and they have almost no gradient flow back there. So they're very, very slow to move. So we had this clever idea. Why don't we just parameterize these tensors with multi-layer neural networks operating on a fixed input? This is a trick I've seen in other papers, and it worked remarkably well. We were able to learn complex transformations in a very speedy manner. So suddenly we have much more complex thing we're learning than the Seale, but we can actually learn it in half the speed. So this is my final architectural diagram of this presentation. This is our final way of doing lifelong learning of an actual real problem. And we're continuously adapting this stable diffusion model. How do we go about doing that? As I mentioned in the recent slide, we have these clever little but tricky little MLP tokens where we replace these tensors that are deep in the model with almost no gradient with multi-layer perceptron models that operate on a fixed input tensor. So what that means is after they've learned through gradient descent what to output, we can delete the model itself and just keep its output result for it. So there's no extra parameter cost, there's zero cost in inference just during training. And because the model is so huge, we actually notice no increase in training time per step when we add these little tokens in there. Just like last time, we have this forgetting regularization with the Seale, but now we have these masks up here. We've masked the binary discrete mask with the Gumbel softmax. And finally, the last key to make it all work is a very simple sparse penalty, where we tell the mask have as few ones as possible so that we only keep ones at the exact precise spots that the LoRa adapter needs to operate on the weight matrix. Yeah, and so we ended up having great performance with this. In our paper, we had up to 50 concepts at a time. We did a mix of people and different types of landmark locations, and we were able to retain the identities and properties of all of these people, even if we went up to 50. And in the top right, it is kind of hard to see all these at once. On the top right is a little easier to digest quantitative results. We showed that the distribution distance between our results and the true training data had the smallest distribution distance compared to all the other methods. And key awesome is we had almost zero forgetting because of the sparsity. So the forgetting column is 0.01. That was a remarkable result here. Let me show you from a different angle. Oh, no, this slide first. So what are we doing here? I mean, this is the cool thing. Like this is real. We can learn this person. We can learn this waterfall a long time later. Then we can go back and generate this person at the waterfall. And then later we can go learn this new person. By the way, these are celebrities. I have no idea who they are. So if you don't have something bad about them, just keep it to yourself. We learn this new person now. You know, at time 50 later, we've added 50 different collections of data, 50 different customized concepts to our model. We can go back and say person 39 and person 1 at concept 24 and have all three of them in the same photo. And we're able to do that. These pictures aren't perfect, which is due more to the backbone we were working with. But this is a great way to have lifelong learning and add concepts over a lifetime of a model without having to continuously retrain the model in order to avoid forgetting. We can come back in the future and generate all different combinations of these people. Caveat, these results, as most generative AI papers are, a little bit cherry picked. But overall, we had a much higher success rate compared to any other methods that we tried for the same benchmark. And my last technical slide of this presentation, this right here is the remarkable takeaway from the method. I'm showing you when training 50 different tasks, when I update a parameter in the stable diffusion backbone, what % of those parameters are being changed and modified from the pre-trained backbone for the very first time. And we see it almost every single task, every single model change we do to the backbone is being modified for the very first time. Meanwhile, like our Seale method, it would have 100 at task 1, and then it would drop down to 0 at task 2 because it modifies every spot, and it would be 2 to 50 are all going to be at 0. But because our adaptations to the model are very precise, very surgical, and very sparse, almost every single modification we have to the backbone is its very first time it's ever been changed. And furthermore, of a prize back to image classification, the work we did earlier in this presentation, our stamina method, this most recent one, and our lore-based methods actually beat all of our prompting methods. So those have been replaced by these stamina adapters. So the cool thing here is this is the solution not just to this problem setting, but it is actually a useful tool for many different problem settings, including image classification. Great, so thank you all for bearing with me. We just have a few conclusion slides. So back to that thesis statement. We claimed that auxiliary replay data and strongly modeled pre-training can replace the need to store training data forever when we want to have lifelong adaptations to a model. We showed in part 1 that yes, pseudo replay data can replace real data. I put the caveat sometimes because we showed it can replace it, but it's not ever a one-to-one replacement of training data. Real replay training data is still going to work better than pseudo data. The same thing with his pre-trained models. We had strong evidence showing that we get really close to the upper bound of performance without storing any replay data at all. But replay can always help there as well. I need to make that caveat here. And lastly with this, the same thing for the Seale papers. We were able to have really good performance with no replay data at all, but the caveat remains that replay is always going to help here as well. In terms of future work, this presentation, we said, hey, memory might not always be there for replay data for lifelong learning models, especially modern machine learning methods that work with real private user data. Can we have lifelong adaptations to models without requiring Meta or Google to store your private user data long term? What if the opposite is true? What if we're working with data that could be stored in data servers somewhere for cheap? This is what we argue what the future of continual learning should be on the other point. Rather than having these fixed arbitrary constraints that exist in the academic setting that says, I need to only pick 5% of the training data and save that forever to replenish my knowledge, we say, hey, memory is cheap. Now, how much replay data can we store? If there's no constraints on it, why is that always a caveat? Memory is cheap. Let's just store all of it in a server somewhere. How much data should we use to replay though? That's the other part. Compute is expensive, not memory. So we should keep in mind how much replay data we should use. We should be using a compute upper bound on that. So our primary goal, what is that? Our primary goal is not what academic papers do, which is with a fixed memory budget, how high can my performance be? We argue that the future of lifelong learning, especially for large foundation models and pre-training, should be how much compute, how expensive will it be for me to achieve that upper bound performance. We say performance is priceless. We should stop having methods with these arbitrary constraints that have large margins between the upper bound and these method performances. And instead, we should focus on always achieving that upper bound, because medical, healthcare, ChatGPT, they want it to perform as good as possible. We should instead focus on how expensive is it going to be to achieve that upper bound. That is what I think the feature of lifelong learning should be when there are no practical memory constraints. So closing remarks, yes, we think that these continual learning is going to be the key to unlocking the future of real world challenges in machine learning. Some examples I just discussed: large language models, personalization, open world detection. Furthermore, we think for the academic setting of continual learning, strong pre-training is actually the beginning of useful applications of our type of studies rather than the end. With strong pre-trained models, we can now demonstrate our continual learning and adaptations upon those to have them lock their full potential to be used out in the real world. And that is my presentation. I would like to first thank my committee. Dr. James Hayes and Dr. Larry Heck are both online right now. Dr. Judy Hoppins in the back. I spent extra time with her. I was a TA for her, and I got to learn a whole lot about her wonderful teaching skills. And Dr. Leonid Karlinsky is from IBM. He's also online. He's been my mentor and manager at IBM, and has taught me tremendous knowledge about deep learning and all the papers we've written together, and become a close friend as well. Dr. Joel Kira, sitting right here, introducing me, telling me to hurry up so we can finish this up. He has been my wonderful advisor throughout my PhD and taught me so much. Yin Chang Su, I think he's asleep now because it's California, but he was a mentor when I started off my PhD. He was who worked with me directly and taught me and got me started on my first few papers, and he'll actually be my boss starting in a few weeks at Samsung Research. And then finally, Dr. Konstantin Dorvelis has also been a strong mentor to me, especially early on in my PhD. I'd like to also thank all the co-authors of this talk, people from Georgia Tech, Samsung Research, where half the papers were with Samsung Research and the other half were with the MIT IBM Watson AI lab. And then of course there's some floater people. Yi Yang used to be at Georgia Tech, she's at Stanford now, and there's IBM and Rice University. If you see these slides later, these were the papers we discussed during this talk. I've also had the chance to work on other papers that were unrelated to this topic, or they were in different venues that maybe weren't strong enough to put in my dissertation, as well as collaborate on some strong papers with lab mates that are listed here as well. And now, finally, Joel, when you backed up 5 minutes ago, now we are at the question slide. So that will end my presentation, and now we can open the floor up for questions. Thank you.
Awesome. So